natural logs. Okay, what I have written in red on the right-hand side, you do not have to write down. These are just kind of some notes of mine to remind you about what E stands for. So with natural logs, we're going to end up using this letter called E, which is about 2.71828. And E was discovered by a mathematician whose name is Euler. So that's how you pronounce E-U-L-E-R. It's Euler. You're going to come across the letter E in a lot of things in future classes. So if it is used in compound interest, probability theory, statistics, it's irrational, which means it is an infinite decimal that does not repeat and cannot be written as a fraction. If you were to graph this in Desmos, y equals 1 plus 1 over x all to the x power, E is its asymptote. So it's going to approach that E, 2.7, so on, but it's never actually going to cross it. It was also discovered that if you add up these fractions, 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial and so on, that sum actually equals E. Now, really quickly, this is called a factorial. So 3 factorial is 3 times 2 times 1. 4 factorial is calculated by going 4 times 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1, and so on. I think you can kind of figure out that pattern. But if you take that interesting sum, it also approaches E. So E is a number that is in a lot of different spaces, so it needed its own letter and its own representation. So the log of E has its own word, and it is a natural log. If you look on your calculator under the log button, there is a button that says ln. That is the natural log button. That is a log that has a base of an E. So ln natural log follows all the same rules and properties as a log. It's just that it's a base E. So a log that doesn't have a base is a base 10, the common log. A natural log, you do not write the E. It's just understood to be an E, and it has a base of E. So let's practice some of our rules that we've already used, but we will use them with natural logs. So create this table real quickly if you need to. Pause this. So our first one is an exponential. E to the x equals 24. So if I were to change this into a log using the log loop, I would have a log with base E, because the base of my exponent is the base of my log, and it would be log base E of 24 equals x. However, we don't write a log base E. The way we write that is natural log. So log base E is actually written as natural log, ln. I always do it cursive. Sometimes I usually do it cursive. So that's an ln in cursive. Why? Who knows? Go for it if you want to, or write ln however you want to. So log base E is ln of 24 equals x. So that's how you would change E to the x equals 24 into a natural log. So if I had the natural log of x equals 58, so natural log has a base of E. We don't have to write it. We just know it's there. So our base of our log is the base of our exponent. So E to the 58th power equals x. So the same log loop as before. So let's go from the exponential right to the correct logarithm. So a log base E, I'm going to write as a natural log of 72 equals x plus 5. And our last one, a natural log, means a base of E. So E to the 32nd power equals x minus 9. So that's how you're going to change in between a logarithmic and an exponential equation. Okay, so it also follows all the same rules of condensing and expanding. So if I have the two natural logs that are being added, addition gets condensed with multiplication. So this is going to become the natural log of 3 times 16, and 3 times 16 is 48. So that's the natural log of 48. Now, if I wanted to figure out what that is approximately in my calculator, I would click that natural log button, which again is under the log button, and then 48 and hit my equals button. You will do some of that on today's assignment. Just like our regular logs, if there is a coefficient can become an exponent. Exponents can become coefficients, and coefficients can become exponents. They can go back and forth. So this becomes the natural log of 63 minus the natural log of, and 3 to the second power is 9. Then, if I am condensing the subtraction of logs, I use division. So this becomes the natural log of 63 over 9, and 63 over 9 is 7. So we have the natural log of 7. If you have where two natural logs have the same part of a fraction, the denominator, then that's something they actually have in common. These are both the natural logs of something over 3. Now, I do want to say that even if the 64 and the 3 could be reduced, you can't. The 64 is part of a natural log and the 3 is not, so you cannot reduce those. What the 3 is they have them in common. It's kind of like adding or subtracting fractions. They both have a denominator of 3, so the denominator of 3 stays. The top of the fraction is the natural log of 6 plus the natural log of x. So if I want to condense addition, I use multiplication, and this becomes 64x. Now we can do more with this problem. We did something very similar when we took our notes on the on properties of logs. So if I don't have a number in front of my natural log, it's like I have a 1 in front of there, which then creates this fraction of 1/3. So this becomes 1/3 natural log of 64x. Coefficients can become exponents, just like our rules for logs. So we can write this as the natural log of 64x all to the 1/3 power. Now we wrote a little note on exponential fractions. We wrote a note last time in our properties of logs that x to the a over b equals the b root of x to the a. So the denominator is our root and the numerator is our exponent. So for this log to the 1/3, the 3 is our root number. So this becomes the natural log of the third root of 64 to the x power. Now what also is interesting about this is that you can actually take the third root of 64. The third root of 64 is actually a 4 because 4 to the third power is 64. So part of this particular problem can become a whole number. Our x can't be cube rooted because we don't know what x is, but we're going to leave it as the cube root of x. So this answer we can use as a fractional exponent. So I would take this as your answer. If you changed it into a root, I would take that. And if you simplified it even further, you could get that. I want you to know how to do all of them, but all of those are possible answers. Okay, now we're going to get into solving. So there are two types of solving log problems. Look at your solving logs notes. Type 1 is log equals log, where there are balanced logs on both sides. It's like they cancel and the rest of your equation is equal. Then there's the log equals a number, in which you have to change it into an exponential. This one is going to become that type 1, where it's log equals log. However, we first need to do some simplifying, because there are natural logs on both sides, but there's more than one natural log on both sides. So on the left-hand side, if I want to condense the subtraction of logs, I use division, and 72 divided by 4 is 18. On the right-hand side, if I want to condense the addition of logs, I use multiplication. Now I'm going to multiply my 6 by x minus 2, but I'm going to distribute. So I'm going to call that 6x minus 12. 6 times x is 6x. 6 times negative 2 is negative 12. My logs are balanced, so I can say that they're already taken care of, they're done, and the rest of the equation is what I'm going to solve. So now I'm just going to solve this for x. I'm going to add 12 to both sides. I'm going to get 30 equals 6x, and I'm going to get x equals 5. Do not forget to look for extraneous solutions. So I don't have an x here, I don't have an x here, I don't have an x here. If I plug in x is 5 here, 5 minus 2 is 3. That's fine. You can take the log or natural log of anything that's positive. You just can't take the natural log or log of anything that's 0 or negative. So it's not an extraneous solution. It's all good. X equals 5. For problem number 9, while I could make this an exponent, I really don't want to have to figure out what m plus 4 squared is. I could. Kind of a little quick reminder, if you're going to square something, that means multiply it by itself, so I would have to do some super distributing. However, in this problem, since this is log equals a number, I have another option. I can divide both sides by 2 instead, and then I don't even have to worry about my coefficient. If you change your variables, that's not an x to an x, I'm totally okay with that. So 4 divided by 2 is 2. So this problem is a natural log equals a number. So I'm going to use my exponent rules, or I'm going to change it into an exponential, and I have a base of e because it's a natural log, so e to the second power equals m plus 4. Now these problems are a little bit different because e is irrational, so it's not a nice easy number. There are 2 different ways to get an answer. Well, one of them's exact and one of them's a decimal. So first, I'm going to subtract 4 from both sides, and I'm going to get e to the second power minus 4 is what my m equals. This is what I would call the exact answer because it's in terms of e. Now, if I wanted a decimal answer, let's just say 3 places, because I believe your assignment today is to the third place, you would, in your calculator, calculate e to the second power minus 4. Now, when you calculate e to the second power, you're going to find the button that you're going to have to use your second button, and it's above your natural log, and it has an e to the x. So it's going to bring up an e with a little caret. You're going to put the 2, make sure you close your parentheses, and then you're going to subtract 4. So if you do e to the second minus 4, you should get about 3.389, I believe, for 3 places. So make sure you're very careful about closing your parentheses. So that is the decimal version, where e to the second minus 4 is the exact version. So I need them both. Let's try one more. Problem number 10. Natural log of x minus the natural log of 9 equals 7. So first I need to condense my natural logs. So the natural log of x over 9 equals 7 because subtraction condenses with division. Now I'm going to use my log loop. So the base of my natural log is an e to the 7th power equals x over 9. If I want to get my x by itself, I'm going to multiply both sides by 9. So 9e to the 7th is my exact answer. And if you plug that into your calculator, you're going to go e to the 7th. Make sure you close your parentheses. Multiply that by 9. This is a very large number. This is 9,869.698. So that is why sometimes having the approximate with a large exponent can be very nice instead of having to write it out. Both of them work. I would take either.